Hi, my name is Simon Ståhlberg. I'm one of the authors of the paper Learning Generalized Policies Without Supervision Using Graph Neural Networks, which I co-authored with Blai Bonnet and Hector Geffner. This workshop paper is a continuation of our main track paper, also presented here at ICAPS 22, and I'll try to quickly point out some of the differences between these two. In our previous paper, we presented a neural network architecture for classical planning, and models are defined using only the predicates of the domain. That is, the models are problem independent and can be used for any problem in a domain. We then use these models to learn optimal policies and show that they generalized to much larger instances. In this paper, we changed our focus from learning optimal policies to learning suboptimal policies with a novel loss function. Since the neural architecture is based on graph neural networks, its expressive power is also well understood, and we show how derived predicates can be used to overcome some of the lack of expressive power. In this paper, we also learn policies indirectly by learning a value function. In our previous paper, the value function predicted the unit distance to the closest goal state. We do not have a similar interpretation of the value functions learned in this paper, since the value can drop by more than 1 in a single transition, but the closer we are to a goal state, the lower the value. As I mentioned earlier, the expressive power of this architecture is understood and is related to C2, which is a fragment of first-order logic, where formulas are restricted to 2 variables. And we can only learn a proper policy if it can be expressed in C2. I will give a simple overview of the loss functions we use in this paper. If a state is a goal state, then the value should be 0. And if the state is not a goal state, then the value difference between it and its best successor state should be either exactly 1 or at least 1. When we restrict the difference to be exactly 1, then we are learning optimal policies. However, when we allow the difference to be greater than 1, then we are potentially learning suboptimal policies. This difference is quite important, since optimal planning might be intractable, but satisficing planning might be tractable. With respect to value-based reinforcement learning methods, they often attempt to learn optimal policies, and we note that such methods will fail when optimal planning is intractable. I will give a rough overview of the experimental results. However, due to space and time restrictions, I will only show a subset of our results. First of all, I want to note that the test instances are much larger, and the goals contain many more atoms. This coverage table is for our learned suboptimal policies, but in the paper we also show coverage results for optimal policies. We see that the coverage is 100% except for logistics and reward, and in the paper we take a closer look at these two domains. The reason why logistics got a relatively poor coverage is that we needed a feature that cannot be expressed in C2. More precisely, we cannot express whether an airplane with a package is at the correct city, and by correct city I mean that the package needs to be delivered to a location in the city. The main issue is the last part, that is the notion of correct city, and we use the right predicates to pre-compute this by composing 2 predicates of arity2. We did not get 100% coverage in rovers because there exist paths longer than the number of layers in the network, and we can only compute paths of length up to the number of layers. So for this domain, for these test problems, the fix is quite trivial. We can simply increase the number of layers. Just to summarize, we did not get 100% coverage for logistics due to lack of expressive power, but derived predicates helped us overcome this. Also, reward did not get 100% coverage due to too few layers. In other words, we were able to give a very precise explanation in all domains we could not learn a proper policy for. So, in this paper, we consider the problem of learning generalized suboptimal policies for classical planning domains, learned from small instances. This is a continuation of our ICAPS 22 paper, which is in the main track. And the main difference is that we learn suboptimal policies instead of optimal policies. And we show how derived predicates can be used in some domains to compensate for lack of expressive power. Thanks for listening.